Okay, today we're going to look at the rational root theorem. That is a really useful theorem. It helps you find all of the possible roots of a polynomial, or at least all the possible rational roots of a polynomial. And remember, a rational number is just an integer over an integer. So the rational root theorem, or the rational zero theorem, says that if you're given a polynomial of this form, f of x is some sum of powers of x, then to find the rational roots, all you have to look at is two parts of this: the constant term and the leading coefficient. So it says that the possible rational zeros are the form p over q, where p is a factor of a naught and q is a factor of the leading coefficient a sub n. Okay, so this is all the these are all the factors of the red number, and these are all the factors of the blue number, and you have to multiply by plus or minus 1. So here's an application. In example 1, we're asked to use the rational root theorem to find all the possible zeros, or all the possible rational zeros for the following function. So we have f of x is 3x to the fourth plus x cubed minus 11x squared minus 9x plus 6. And again, the great thing about this is it says that you just need to look at the 6 and you need to look at the 3, and then the theorem says that the possible rational zeros are the following set. We have plus or minus 6, so that would be 6 over 1, plus or minus 3, plus or minus 2, or plus or minus 1, over the possible factors, over the possible factors of the leading coefficient, which would be plus or minus 3 or plus or minus 1. Okay, so that's just a shorthand way of listing all those. And now I want to go through and actually figure out what those are. And remember that, let me just say that this is, we have factors of 6 over factors of 3. Is another way of writing what I just wrote down. Okay, so let's simplify this a little bit. This says that we have the following list. Okay, so if the bottom number is 1, then we're going to get plus or minus 6, plus or minus 3, plus or minus 2, or plus or minus 1. And if the bottom number is a 3, then we're going to get plus or minus 2, which we've already written down, or plus or minus 1, because plus or minus 3 over 3 is plus or minus 1. And then we could also possibly have plus or minus 2/3, or plus or minus 1/3. Okay, and so again, this is the list of all possible rational roots. But not every one will actually be a root. Remember that we use 0 and root interchangeably. So not everyone will be a root or 0. So to find out which ones are, you actually have to do guess and check. So guess and check, and you want to use synthetic division. Probably is the fastest way to do that, to see if one is actually a root. So what we figured out so far is if you just look at this polynomial and you look at the leading coefficient and you look at the constant term, then you're going to get a total of, let's see here, 1, 2, 3, 4, 5, 6, 12 different possible rational roots. And of course it's a polynomial degree 4, so at most 4 of these could actually be roots. So not everyone will, but at least you know where to start, and these are the numbers that you'd probably try and check. Okay, in problem 1, I'd like you to take a second and try and do like we just did in the previous example, and then we'll check our work in a minute. So pause the video, work through the problem, and try and answer the question. Okay, so welcome back. Now what we're going to do is apply the rational root theorem to try and find all the roots of f of x. So again, the leading term is 2, or the leading coefficient is 2, and the constant coefficient is 5. So the possible rational roots are let's see here, factors of 5 over factors of 2. And remember that if 1 is a factor of 5, so is negative 1. So you have to take plus or minus all these numbers. Okay, well that's going to be plus or minus 5 or plus or minus 1 over plus or minus 2 or plus or minus 1. And to write this out nicely, it should be either plus or minus 5, plus or minus 1, that's if the denominator is 1. And if the denominator is 0 or is 2, then you're going to get plus or minus 5/2 or plus or minus 1/2. So in this case, we only have 8 roots to check, or 8 possible roots to check. All right. So now we're going to actually apply this theorem to actually find all the rational roots. So it says here, to solve this equation, you want to list all possible rational roots, use synthetic division to test the possible rational roots, and then find an actual root, and then finally use the quotient from the previous step to find the remaining roots and solve. So this is going to take a little while. Alright, so we're looking at f of x is x cubed plus 8x squared plus 9x minus 18, and we're setting that equal to 0 and solving. And remember that the coefficient here, the leading coefficient is 1 in this case. So step 1, to list all the possible rational roots. We get this is plus or minus all the factors of 18. So that'd be 18 or 9 or 6 or 3 or 2 or 1. So there again, I just factored 18, and I can either factor as 18 times 1 or 9 times 2 or 6 times 3, and I took the plus or minuses. And then because the leading coefficient is 1, these are all the possible rational roots. So I have 1, 2, 3, 4, 5, 6. I guess I have 12 different possible rational roots. And now we need to guess. And hopefully we'll get lucky and guess an actual root. So we'll guess, we'll do synthetic division, and if we guess one of the roots, then we'll get a remainder of 0. If we guess wrong, then we'll get a remainder that's not 0, and that'll tell us we have to go back and try a different value. So let's just try something and hope that we get lucky. So I'm going to guess maybe that 1 is a root. And remember that if 1 is a root, that's the same as saying that x minus 1 is a factor. Okay, so to do this, we're going to do synthetic division. So let me write down. I have an x cubed, an x squared, an x1, an x0. So I've written down my placeholders. And I'm checking to see if 1 is a root. Oops, I didn't write down my coefficients actually. Let me write down the coefficients. My coefficients are 1, 8, 9, and negative 18. Okay. So I bring down the 1. 1 times 1 is 1. 8 plus 1 is 9. 9 times 1 is 9 plus 9 is 18. 1 times 18 is 18. And negative 18 plus 18 is 0. Okay, great. So I guessed right. And I got a remainder of 0. So 1 is a factor. Or 1 is a root. X minus 1 is a factor. Okay, so that's great because that's told me that I've at least factored one linear factor out. Now I can keep going. Okay, so what I just found is that f of x can be written as x minus 1 times x squared plus 9x plus 18. So I figured out one of the factors, and now I'm going to apply the rational root theorem to the x squared plus 9x plus 18. And because I have 1 and 18 again, I have the same exact possibilities. And so I'm going to guess again, and this time I'm going to guess, well, just looking at that, I can kind of see that this is going to factor okay. I'm going to guess negative 3. Or, yeah. I'm going to guess that 3 is a factor. No, negative 3 is a factor. Okay, so actually if you just eyeball this, what you can see is that this is probably going to be x plus 3 and x plus 6. And so that's telling me that x equals negative 3 would be a root. So let me just go through and do the synthetic division in case you didn't see that. But again, I'm just going through this list and picking a value that looks like it might be a factor. And so if I do this, I get 1, 9, 18, and I bring the 1 down, I get negative 3 here, I get 6. Negative 3 times 6 is negative 18, and so I get a remainder of 0. So there you can see that my remainder is 0, and that actually tells me that x plus 6 is my remaining factor. So what I found is that f of x factors is x minus 1, x plus 3, and x plus 6. Okay, and I've done that. You could either just look at this quadratic and factor it in your head, or you can do the guess and check using synthetic division. You should get the same answer either way. Okay, so it says here to find all the possible rational roots. So since f of x factors like so, my rational roots, or my roots are x equals 1, x equals negative 3, and x equals negative 6. And you get those by just setting each one of those linear factors equal to 0 and solving for x. Alright, so there's my final answer. Alright, now it's your turn to do problem 2. And again, I want you to pause the video, go ahead and go through the same process that we just went through, and check your work when you're all done. Okay, so now I'm looking at the last coefficient. The coefficient of the constant term is 10, or negative 10 actually, and the leading coefficient is 1. So the rational root theorem says that the possible rational zeros or roots are plus or minus 10, plus or minus 5, plus or minus 2, and plus or minus 1. So I have 8 possible numbers to check. Okay. Again, those are just the factors of 10 over the factors of 1. Now, step 2 of this process says to guess and check using synthetic division. And if you're like me, you're probably going to guess x equals 1. And you want to see if that's a root or not. Well, let's see. To do that, you would say, okay, if x equals 1 is a root, that would be doing negative 1 here. No, that would be doing just x equals 1 there. And I'd have x cubed, x squared, x to the 1, and x to the 0 as my placeholders. And I'm plugging in the coefficients. 1, negative 4, 9, negative 10. Okay, and now I do the synthetic division, and I get 1. 1 times 1 is 1. Negative 3, 6, 6, negative 4. Okay, and again, we've seen that we can factor this as 1 times x squared minus 3x plus 6, but we get a remainder of negative 4. And so that tells us that x equals 1 is not a 0. And so we were wrong. So we guessed x equals 1, and we guessed wrong. Dun, dun, dun. Okay, well, let's try a different one. Let's try x equals 2. If I guess x equals 2 as a root, then I will actually, it will be right. Let's try this. So we got 2 here, x cubed, x squared, x1, x to the 0, 1, negative 4, 9, negative 10. Okay, bring the 1 down. 2 times 1 is 2. Negative 4 plus 2 is negative 2. 2 times negative 2 is negative 4. 9 minus 4 is 5. 2 times 5 is 10. Negative 10 plus 10 is 0. So in this case, I see that I actually get a 0. So I have x squared, x1, x0, and a remainder of 0. Okay? So what this told me is that f of x equals x cubed minus 4x squared plus 9x minus 10 factors as x minus 2 times x squared minus 2x plus 5. And now I can go ahead and find my other two factors of the x squared minus 2x plus 5. And the rational root theorem now tells me that it's either going to be plus or minus 5 or plus or minus 1. So factoring actually made this problem a little bit simpler, because now I just take the plus or minus of the 5 over the plus or minus of the 1. So now I'm either going to guess 5 or 1. Well, we already guessed 1, that didn't work. And actually, if you guess plus or minus 5, or if you guess negative 1, none of those work. Okay, so I want to say that to save us all some time, we'll say, oops, we checked all these and they didn't work. Okay, and by these I mean we checked all of the plus or minus 5 or plus or minus 1. But all is not lost, because this is a quadratic equation. So if we didn't want to just try and factor these into rational roots, we could just apply the quadratic equation and solve for the remaining roots. So we have a is 1, b is negative 2, and c equals 5. So x must have been 2 plus or minus the square root of 2 squared minus 4ac all over 2a. And what I get is that x is equal to 2 plus or minus, 4 was, or c was 5 there. So this is 4 minus 16, or 20, which gives me negative 16 all over 2. So x is either 1 plus or minus, that would be 4i over 2, so 2i. Okay? So the takeaway here, or the conclusion, is that I have 3 roots. Only one of them is a rational number. The other 2 are complex. So the conclusion is x equals 2, x equals 1 plus 2i, and x equals 1 minus 2i are the roots of f of x. And an equivalent way of writing that is that f of x can be factored as x minus 2 times x minus 1 plus 2i times x minus 1 minus 2i. Okay, so you can either write it down as a factor or a product of linear factors, or you can just list all the roots. And those are kind of the same thing. Okay, so we've kind of seen a very important property of polynomials in the last example. Not all the roots are going to be real numbers, but if I allow complex numbers, all of the roots will be either real or complex. And you notice in this last example that 1 plus 2i and 1 minus 2i were both roots. So those are complex conjugates of each other. And so this is the content of this next little subsection. It's kind of like the fundamental theorem of algebra that says that if you have an nth degree polynomial, then you know all the roots are either real or they're complex, and they're going to show up as complex conjugates. Okay, so if you have an nth degree polynomial, then you're going to have n linear factors, or in other words, you're going to have n roots. So let's see, in example 4 it says we're asked to just find an nth degree polynomial where n is 3. So we're looking for an nth degree polynomial function with real coefficients satisfying the given conditions. So we're given that 4 and 2i are zeros, and we want f of negative 1 to be equal to negative 50. Okay, so let me just write this down. F of x is degree 3, so we know it's a sub n x to the third, so a sub 3x to the third, plus a2x squared plus a1x plus a naught. But we also know that it should be written as maybe x minus, we know that x minus 4 is a 0, and or is a linear factor, and we know that x minus 2i is a linear factor. And then if you remember that the complex conjugate of a complex number is also a 0, then we must have that x plus 2i is a 0 as well. So let's see here. What we know is that this factors this way, and that we might have some coefficient out front. So I'm writing this as like a sub 3, I guess. Okay. Okay. So the keys here are remembering that 2i and negative 2i are complex conjugates. So that's one of the keys. And now what we want to do is we're given this condition that f of -1 is equal to -50. So we're going to use that to solve for that a sub 3. So what I have is I have a sub 3 on the left-hand side, and I'm plugging in -1. So I have -1 minus 4, and -1 minus 2i, and -1 plus 2i. And I'm supposed to solve for a sub 3 to figure out what that leading coefficient is. Okay, well, let's see here. This is -50 equals a sub 3 times -5, and then I should actually FOIL that right there. I'll get 1 plus 4. Okay, that's another property of complex conjugates, is that if you multiply two complex conjugates, then it's the same as adding up the a squared and the b squared. So in general, a plus bi times a minus bi is always equal to a squared plus b squared. You can just check that, because you're going to get a times abi and negative abi, so the products of the a's and b's will cancel, and then you'll get a squared, and you'll get negative b times I squared, which is b squared. Okay, so it looks like I have -50 equals a sub 3 times -25. So then that means that a sub 3 is 2. Okay, so what that I've just figured out finally is that f of x equals 2 x minus 4 x minus 2i and x plus 2i. So there's only one polynomial of degree 3 that will satisfy the initial conditions that 4 and 2i are zeros, and f of -1 equals 50. So that's my final answer.